Good morning. My name is Abbas Abdullahi Auta, a technologist in charge of Physics 227, that is experimental physics 4. Alongside, there is an academic staff in charge of the course in person of Mr. Usman Sarki Muhammad. Physics 227 is an experimental physics 4 that is taken by three different departments, that is BSc Physics 200 level, SLT Physics option, and education students in sciences 200 level. Introduction of the course. The introduction has to do with the basic concept of measurement, data, and error analysis. By definition, measurement is a statement of result of human operation of observation. One does not generally make measurement for his own satisfaction, but he is obliged to communicate his experimental results to other people. But the reliability and authenticity of measurement depends on one's reputational profession. There is this saying that nevertheless, no experimental evidence is absolutely true. Of course, experimental evidence are true, but the saying says no experimental evidence is absolutely true. But before then, I have an example to present. If you invite a roadside painter and ask him how many gallon of paint or quantity of paint will be enough to paint this particular office, he will give you an estimate of a particular quantity. And in that estimation, there is a possibility that the quantity will be less than that, the quantity could be more than that, or in some cases, it may serve that same purpose of painting exactly the size of this office. But if you meet an engineer who specializes in all these areas, and you give him or present to him this same question, he cannot just give you an estimation. What he will do is he uses his what? Measuring device to measure the length, the breadth, and all corners of the room. It is from there he will come up with the exact quantity of paint that will be enough to paint this particular office. Apart from that, if you meet a tailor with your material and you want him to sew a cloth for you, he cannot just look at you and say, okay, you can go, I will sew it. No, he has a measuring device, which is a tape. He will measure you so that at the end of the day, by the time he finish sewing your cloth, it will size you very well. The same thing that is applicable to tilers, people who put tiles in rooms, houses, and other places. They don't just give mere estimation. They use their measuring devices to measure the length, the breadth, and the size of wherever they are supposed to do the tiling. They give you the estimation based on what they have measured. When you go to the market, you get the tiles, and when you bring it, you discover that it fits or it is enough for that particular room. So what we are trying to pass across here is the importance of measurement. Then back to what I was saying about no experimental evidence is absolutely true. Of course, yes, no experimental evidence is absolutely true. No matter how you are good in taking measurement, even if you are a professor in taking measurement, whether you like it or not, you must come across error because of this saying no experimental evidence is absolutely true. And there are factors that contribute to these experimental errors. Some of these factors include the skill of a researcher. As a researcher or as a person who is carrying out an experiment using instrument or device or equipment or machine, you may lack a particular skill to render that operation appropriately. So that also is a weakness. Secondly, we have environmental factors. That is why in the lab, there are some equipment or instruments that are not kept in an open lab. They are taken to the instrument room where measurements are taken. Why? Because the temperature, the humidity in that instrument room is being controlled to avoid or to reduce error to the barest minimum. That is number two. And thirdly, we have errors that are associated with these measuring devices. That is why in the lab there are commonly used devices or instruments that are used in the lab. The devices themselves come along with error. We'll look at that in the next slide. Then we also have theories that are behind some of these experiments. The theories themselves are not certain. So all these are factors that contribute to error in measurement. That is why the saying goes that no experimental evidence is absolutely true. We have types of experimental errors like the instrument calibration. The observer is here dependent on the scale of instrument for the accuracy of his measurement. For example, a meter rule that is bent. In the course of production of meter rules, maybe from the company, industry, or factory, you discover that, especially the wooden type of meter rule, you discover that one of the meter rules among the hundreds that were presented, maybe one is bent. So if you are unlucky to use that meter rule that is bent in carrying out your experiment, you are bound to come across error. So this serves as one of the types of errors that we're having. We have instrument reproductivity. Even after calibrating an instrument under certain set of circumstances, mechanical defects can still occur, which influence the readings and also affect the value of calibration. We have the observer skills. Just like I have explained, as an observer, as a researcher, if you lack certain skill, you may not be perfect in handling this equipment in terms of operation. So for that reason, you also contribute to error. So this one also serves as one of the types of experimental error. We have the miscellaneous errors. These are usually due to fluctuations in temperatures and humidity, variations of instrument support. Just like I've explained that some instruments are taken to instrument room where the temperature of that room is being controlled so as to reduce error to its barest minimum. We also have the fitness of scale division or sensitivity of measuring instrument. We have the random error. These are the error which result as a matter of chance. They occur due to repeated measurement of the same quantity which give rise to different values. Then we also have the systematic error. This type of error refers to a perturbation which influences all measurement of a particular quantity, e.g. a meter rule used for a particular measurement may be shorter than normal. Just like I've explained that of a meter rule that is bent. In the course of mass production, you discover that the meter rules may not be of the same height. And of course, we know that the standard measurement of a meter rule is 100 centimeter, which is equivalent to 1 meter. So you may discover a meter rule that is not exactly 100 centimeter. Maybe it may be shorter with some 0 point something centimeter. So if you use those kind of meter rule in your experiment, definitely you are bound to come across error. For that reason, this serves as a systematic error and is part of the types of error we're having. Now we move to maximum possible errors of some commonly used laboratory instruments. Just like I have said, and I mentioned that we are going to look at some commonly used laboratory instruments that are associated with errors. That is why you cannot use those laboratory instrument and avoid error in your measurement or in your readings or in your results. But what we expect is the errors that are associated with this commonly used laboratory instrument are very small, but they are not just avoidable. We have the vernier caliper, which is also commonly used in the laboratory. It has an error that is associated with it of 0.1 millimeter. We have micrometer screw gauge. It has an error that is associated with it of 0.01 millimeter. We have the stop watch. It has an error that is associated with it of 0.2 seconds. We have the stop clock. It has an error that is associated with it of 0.5 seconds. We have the thermometer, which has an error that is associated with it of 0.20 degrees Celsius. We have the meter rule. It has an error that is associated with it of 0.5 millimeter. We have the balance. It has an error that is associated with it of 0.1 gram. Then we have the standard moving coils. These standard moving coils include the ammeter and the voltmeter. And of course, we know that the ammeter are used to measure small amount of current, while the voltmeter in the lab are used to measure small amount of voltage. So the error that is associated with these moving coils, that is the ammeter and voltmeter, are not uniform, but it is 2% of the maximum scale reading, because the moving coils have different scale reading. There are some moving coils, ammeter and voltmeter, that ranges from 0 to 5. There are some that ranges from 0 to 10. There are some that ranges from 0 to 15, and there are some that ranges from 0 to 15, 0 to 20, I mean. So you don't expect the maximum possible error on these moving coils of different ranges to be the same. So that is why it is stated here that 2% of the maximum reading. So the moving coils that range from 0 to 5, the maximum possible error is your 2% of 5. That will give you the maximum possible error. The moving coil that ranges from 0 to 10, the 2% of 10 gives you the maximum possible error. Likewise, the moving coil that ranges from 0 to 15, 2% of 15 gives you the maximum possible error of those moving coils. The same thing is applicable to moving coils that ranges from 0 to 20. So 2% of 20 gives you the maximum possible of those moving coils. But unless otherwise stated, the above can be used in every experiment or measurement. And still on the measurement, still on the saying that no experimental evidence is absolutely true, I'll give us a true life example, which we are all used to, especially the married men or women. If a woman is pregnant or a wife is pregnant, normally she do go for antenatal care. And in this antenatal care, she undergoes ultrasound examination, or what we are used to as what scanning. And the essence of this scanning is to checkmate or examine the well-being of this pregnant woman and the well-being of the unborn baby. So in the course of this ultrasound scanning that pregnant women do go to hospital to undertake on periodic level, there is what we call expected delivery date on the result of the ultrasound scanning, or what is called EDD. So you discover that there will be a date the examiner will reflect on her result. But the truth about the result is, it is not that day that she see on the ultrasound scanning that she is expected to give birth. That is why it is called expected delivery date. It is not stated delivery date. It is called expected delivery date. Why? Because the machine itself has error that is associated with it. That is why the machine cannot categorically state the day she will give birth. Even though there are some rare cases where some pregnant woman, maybe 0.001%, where some pregnant woman can give birth on that same day that is reflected on the ultrasound scanning. But in most cases, the woman gives birth 2 weeks before the date or 2 weeks after the date. So this is as a result of errors that are associated with the machine, which cannot categorically state the date, exact date, when the woman will give birth. And even if it states the date, the machine cannot describe the nature in which she will give birth. Could it be in the morning, in the afternoon, or at night? Or how will she give birth? Could she give birth herself, or through CS, or through whatever means? The machine cannot state that. The machine cannot also present in the result the amount of blood she will lose or the pains she will incur in the course of delivery. So all these are weaknesses of the machine, and it agrees with the saying that no experimental evidence is absolutely true. Then we have linear graphs. So in the course of this practical course, we are going to look at graphs that are linear, because in physics it is easy to deal with linear graphs, that is straight line graphs. But in the case where we have curve graphs, what we normally do is we try to linearize the curve graphs so that it will be easy for us to deal with. The first linear graph we have here is a linear graph that has to do with y is equal to mx. The line of best fit emanated from origin. The ordinate is our y-axis. The abscissa is our x-axis. And we have a slope, or what it is referred to as gradient in mathematics, that is denoted with m. This is the first linear graph we have, with this equation that is associated with it. Then the second linear graph we have is y is equal to mx plus c. In this case, it has the ordinate axis, which is y, has an intercept. And an intercept is a line that cut across the ordinate or the y-axis. So that is the difference between the first one we have, which is the y is equal to mx, and in this case we are having y is equal to mx plus c. So plus c here is the difference between the first one and this very one we are having. And of course, it also has a slope, which is also a positive slope. And the abscissa, which is the horizontal axis, is also denoted with small letter x. Then the third linear graph we are going to look at is y is equal to c minus mx. In this case, the ordinate has the y-axis, the abscissa has the horizontal axis denoted with letter x, and as usual, it is also accompanied with a right angle triangle, which is a slope. But in this case, we are having a negative value of slope because the nature of the slope is looking at the other direction. Then we have the fourth nature of graph, which is given as y is equal to minus mx. But the first one we had was y is equal to mx. So the difference between the first one and this fourth one we're having is the first one has a positive slope, while in this case, the fourth one has a negative slope. So as usual, the ordinate give rise to the y-axis, the ordinate, the abscissa, give rise to the horizontal axis, but in this case, the slope is a negative slope. Then we have the fifth nature of straight line or linear graph. In this case, the equation gives rise to y is equal to mx minus c. Minus c because the intercept now cut across the y-axis or the ordinate, but not on the positive line. It cut across the vertical axis on the negative line. So that is why we are having y is equal to mx minus x. As usual, the y-axis give rise to our ordinate, the x-axis, which is the abscissa, while we have our m, which is the slope. Then the curve graphs, just like I have said, there are there are ways in which you linearize or you transform a curve equation to its linear equivalent for simplification. So we have an equation of a curve graph, and what we will do to linearize it or transform it to its straight line equivalent is to square both sides. Here we have t is equal to 2 pi l/g. So if we want to linearize it or simplify it in such a way that we can use it properly, what we'll do is we square both sides. So t is equal to 2 pi l/g. We square both sides. When we square both sides, we are going to have t square is equal to 4 pi square l/g. So we now transform it this way. So at the end of the day, we are going to have t square is equal to 4 pi square slash g l. So what we do, what we do here is we only shifted the l to the other side, so that at the end of the day, we are going to have an equivalent equation of y is equal to mx. Our y is equivalent to t square. Our m, which is the slope, is equivalent to 4 pi square slash g. And our L that we have shifted to the other side is equivalent to our x. That is why in simple pendulum experiment, where we are to determine the acceleration due to gravity of a pendulum bob, small letter g, our slope is equivalent, our slope m is equivalent to 4 pi slash g. And of course, our 4 is constant, our pi is constant, and also our g is what we will make as a subject of the formula to look for our acceleration due to gravity. Then we also have another example here of a curve line equation, which is v is equal to kf raised to the power of n, where k and n are constant, v and f are variables. So what we do here to simplify or transform this curve line equation to its linear equivalent is we now look for the log of v, which is equal to log f plus n log f. At the end of the day, we are going to be left with log v. Now, if we use in the law of indices, as we are aware right from our secondary school days, here we are going to have n log f plus log f. So if you look at this equation, our log v is equivalent to our y-axis, which is the ordinate. Our n log f, our n is equivalent to our m, which is the slope. Our log f is equivalent to our x, which is the abscissa axis, and our log k is our intercept on the vertical axis. So this is the nature of the graph, just like I have explained from the beginning. So pertaining the experiment, we have experiment 1 up to experiment 13. So the first experiment has to do with measurement of height of a ceiling, because in this experiment it involves mechanics, optics, and electricity. So the experiment that has to do with measurement of height of a ceiling, at the end of the day, we are expected to see a nature of graph or our line of best fit on our graph that cannot cut across the vertical axis. Why? Because this has to do with inaccessible height. Because we are trying to assess a height that is not accessible. So definitely the nature of graph will not cut across the axis. It will move sideways. No matter how you try to make it, it will not cut across the axis. To show you that you are at the right track of the experiment. So in the experiment, there are apparatus that are involved: record stand, stop clock, thread, meter rule, and clock. In experiment 2, we have experiment that has to do with a simple pendulum, simple harmonic motion with spiral spring, and Hooke's law. And of course, we are all aware of Hooke's law, where we have a load that has to be directly proportional to the extension on the spring. So in this experiment, apparatus like helical spring, plasticine, retor stand, and clamp, meter rule, way hanger, and masses and stop clock are used. We have experiment that has to do with compound pendulum, and the apparatus involved in this experiment include the meter rule with a small hole, the retor stand, the clamp, the optical pin, and the stop clock. We also have an experiment that has to do with the focal length of a concave mirror. But in this case, we are using the no parallax method. Apparatus involve a concave mirror, a sheet of paper, pins, retor stand with clamp, and boss head. We also have an experiment that has to do with focal length of a converging lens. And the aim of this experiment is to determine the focal length of a convex lens by illuminated object method. Of course, we have different methods, but in this case, we are using the illuminated method. And the apparatus involve a convex lens, meter rule, the ray box, which is our source of light, the white screen, lens holder, and the optical bench. Then we have the resistance of a wire. So because at the end of the day, we are going to determine the resistance of a particular wire. So the apparatus involved are the resistor, the crocodile clip, the plug key, the 2-volt accumulator, ammeter, and a constantan wire. Then in this very course, we also have experiment 7, which has to do with the electronic aspect. We are going to identify color code of electronic components like resistors, capacitors, and other commonly used laboratory components. Experiment 8 has to do with symbol of electrical and electronic components. Of course, in a circuit, if you want to interpret a circuit, you interpret it by looking at the symbol and identifying them. So we are going to look at these symbols that appear on our electrical and electronic circuit with a view to identifying them. Then we will also look at experiment 9. Experiment 9 has 2 parts, the 9A and 9B. 9A has to do with turns ratio of a 2-coil transformer, and the 9B has to do with the iron losses of a transformer. And of course, we know that in a transformer, there are losses that occur. The experiment 10 has to do with the determination of internal resistance of a 12-volt battery. Experiment 11 has to do with determination of load characteristics of that same battery. Then 12, we have the determination of load characteristics of a transformer. And the last part of the experiment has to do with measurement of potential difference across a wire.